Thanks for being here today. Welcome to campus. Glad to have you all. Classes start next week, or tomorrow actually. Classes start tomorrow. So we're here a day early. So today I'm going to talk about PFAS. We're going to look at characterizing extractable organic fluorine as an indicator for total PFAS in water reuse scenarios. So this presentation could really go in the wastewater or the water section. We're reuse, so we're kind of merging the two. So put on your drinking water hat, and then we'll go into your wastewater hat. So before we start, let's talk about water reuse and what it is. So non-potable reuse is where you take wastewater treatment plant effluent and you use it for irrigation, you use it for industrial purposes, or use it for ag. So that's non-potable reuse, also termed purple pipe, because it's literally delivered in a purple pipe, if you've seen it out west. We typically don't have it as much in the deep south. And then for potable reuse, there's three different kinds. The one that you're probably most familiar with, is this de facto. What is de facto? It's where one city A uses the water, sends it through the wastewater treatment plant, sends it to the stream or the river. Downstream, another city will then use that water for their drinking water. De facto potable water reuse. So that's what you typically think of. You probably just maybe didn't know the name. The second one is indirect potable reuse, where you have the wastewater effluent going to a lake or an aquifer system, and then it's gone to the second city for their drinking water. So this is a planned reuse scenario, but there's an environmental buffer in the middle. So that's indirect water reuse. And then our third scenario would be direct potable reuse, where you go from the wastewater treatment plant to an advanced water purification facility straight to the city. So essentially the wastewater treatment plant and the water treatment plant are the same building, and then there's no environmental buffer. That's direct water reuse. So now you know the terms, and we're all on the same page with the different sectors. And then now let's get on the same term with PFAS. So PFAS are a chemical structure developed in the 1940s. It has this carbon backbone with fluorine atoms around the carbon chain. Depending on the length of the chain, short chain or long chain can be to determine how it impacts your health. It's a very hard bond to break, so they're considered forever chemicals, meaning they're hard to break down. They've been detected in rainwater in Antarctica, so it's a very, the bond is really strong and it's good at its job. So it's been used in a lot of technologies. Two of the most common PFAS chemicals are PFOA, this one here, and then PFOS. So these two were actually outlawed in 2006 in manufacturing, so almost 20 years ago, but they're still showing up because they're forever chemicals. They're hard to go away, so we are still dealing with them today. Depending on the functional group, the head of the carbon fluorine chain will give the PFAS the different characteristics, and if it's PFOA, PFOS, Gen X, that can vary between the different PFAS chemical compounds. The problem with PFAS. So this infographic you've probably seen in the different just advertisements and different sectors, but PFAS can impact humans adversely. So cancer, increased links to cancer, reproduction issues, low birth weight for children, higher cholesterol, issues on just the human population. We get it through Teflon cooking pans. If you have that Teflon pan to cook your eggs in it, it can leach from that. You can get it from your drinking water. Lake Tuscaloosa, we're good. We don't have PFAS in the Lake Tuscaloosa, but depending on where you live, you may have PFAS in your drinking water. You can get it from the clothes that you wear. So if you wear water-resistant clothing, it was probably made with PFAS material. Patagonia, they're a company now that has said they're not going to use PFAS in their water tech gear. So if you're looking for a new rain jacket, go buy one that doesn't have PFAS in it. So there's different companies that are looking at not using PFAS in their products to help this problem. And then, of course, PFAS can be in the air and dust. So they're forever chemicals because they just basically are really hard to degrade, but which make them really good at their job. Whenever you put them in a manufacturing process, they're strong, they're durable, they're strength, so they're good at their job, so that's why they're so prevalent. But for us, they're an issue. For the water and the wastewater sector, they are an issue because we don't want them in our water. So the EPA back in March 2023, so almost a year ago, said proposed limits for 6 different PFAS compounds for drinking water. So this would go into the national primary drinking water regulations. And if this happened, then water treatment plants would have to do 3 things. They would have to monitor for those PFAS. They would have to notify the public of those levels. And if they were above certain concentrations, then they would have to put in the technology to treat to reduce those levels, and they would have to be in compliance within 3 years. So this is huge because the technology to remove PFAS is expensive, and then again, for the regeneration as well. So for the 6 compounds, 2 of them have a maximum contaminant level. So PFOA and PFOS, these 2 have a maximum contaminant level of 4 parts per trillion. The method reporting limit is basically 4 parts per trillion, so it's extremely low. The maximum contaminant level goal is 0. That means that the maximum contaminant level goal is how much in the water would not have an adverse impact on the health, and it's 0. So you pretty much, they said you don't want any PFOA or PFAS in your drinking water. And then they have these 4 PFAS compounds that they said, okay, we're going to regulate these as a hazard index. You need to measure them in your water. You put them in this equation here, and then if that hazard index is less than 1, you're okay. If it's greater than 1, you're going to need to reduce those levels. So the EPA has proposed for 2 PFAS compounds, PFOA and PFOS, to have actual maximum contaminant level of 4 parts per trillion, and then the other 4 add them together for a hazard index to be less than 1. So this regulation is still going on. They should be finalized soon. Then once it is, utilities would have 3 years to come into compliance. All good so far? Okay, great. So now the EPA also has is the unregulated contaminant monitoring rule. So this rule, UCMR 5, is the one that we're currently in. It basically says that if there is a contaminant out there that maybe is showing up in drinking water that we maybe should regulate, let's measure and sample utilities to see if it's present at a concentration that we should regulate. For a contaminant to come into regulation, it has to meet 3 things. It has to be harmful to humans because we're drinking it. It has to show up in the water, and it has to present a meaningful opportunity to monitor and to regulate. So those 3 things. So the unregulated contaminant monitoring rule helps us get data. For these compounds, it helps us go take to utilities to sample and to figure out, are these contaminants actually showing up? So the rule is, it's a 3-year-long data analysis. So started January 2023. So we've done the first year. They have 2 more years. On this UCMR 5, there are 30 compounds. 29 of them are PFAS. And then there's lithium. So we're going to focus on the 29 PFAS. I'm going to show you some of that data today. So far in the past year, they've collected 15% of all the data they're going to collect for this UCMR 5. So the types of system that they're going to collect from is going to be small, very small, and large. And they'll collect from 11,000 public water systems. So I'm going to show you some data from the past year that they've collected. It's only 15% of the overall data they'll continue to collect the next 2 years. So from the different 300 samples that have been reported so far, half of them are in small systems, half are large systems. So they haven't even, or they may have collected, but they have not shown to the public any data from very small systems. And then of the source water, the green is groundwater, the purple is surface water, groundwater under the influence of surface water, and then the very top is like a blend of 2 different types of surface water. So this is the map. Oh, you can see this map, great. So the map of the US, and this shows PFAS detection in the different states that would be above the minimum reporting limit. So for the UCMR 5, they have the 30 compounds. The minimum reporting limit is the value that, with 95% confidence, 75% of utilities, or 75% of labs can detect that level. So it's not necessarily the same as the the maximum contaminant level goal, but it was pretty similar. So for the PFAS, it's anywhere between 2 parts per trillion to 20 parts per trillion for each of the 29 PFAS contaminants on this list. So what this map is showing you is that these states, 73%, their map, the ratio, it's 0 to 73% PFAS detection. So that's saying that the percent of public water systems that showed a PFAS level above that minimum reporting limit value. So you can see in the Northeast has a lot of darker blue. So they're having a lot of public water systems that are having PFAS detections above that minimum reporting limit. But the states with the highest population density where the most people are affected would be California, Texas, and Florida. So again, this data is just from the past year, 15%. So it'll evolve over the next 2 years as the data is continued to be collected. So these are the 29 PFAS contaminant, the percent of the sample over that minimum reporting limit, and then as well as that average concentration. So here, the 2 in red are the 2 that had that maximum contaminant level of 4 parts per trillion. So PFOA and PFOS. So you can see they're showing up, and this is parts per billion. What was the regulation in? Trillion. So multiply this number times 1,000. So it would be for PFOS, it would be showing up as about 10 parts per trillion. PFOA would be 8, and the goal maximum contaminant level was 4 parts per trillion. So again, this is only 15% of the data. We still have a lot more to learn, but it's good insights into what's actually happening. And then the orange would be those 4 contaminants that you would add together for the hazard index. And if you look at these 6 specifically and where they're showing up, see these maps. So the top left is hard to see because it's not shaded in as much. But PFOS and PFOA were the 2 that had that maximum contaminant level, and then the other 4 you would add together for the hazard index. And so this is a percent of public water systems that have a detection above the MCL. EPA has this PFAS analytical tool, so you can go on, and it's a live website that they are updating with the data as it's brought in. So you can go and look PFAS, and they actually have water samples, tissue, air, soil, sediment, so you can toggle on and off the different categories that you want. So we're in Alabama, we're in water, so that's what we looked up. So you can look here, you see the state of Alabama, you can see the different, if it had non-detect, it's a hollow white circle. So public water systems that had a non-detect show up there, and then orange or brown-green color if it was above the minimum reporting limit. And then it also can show you different sources in the area. So it's a really cool tool to look into and that the EPA put out that they'll continue to update as it goes. And you can scroll down and it showed you all the different utilities too. So this was very nice. So now kind of transitioning more into the wastewater, the EPA also proposed regulations for PFAS in biosolids. So land-applied biosolids, in 2021, 43% of biosolids in the US were land-applied. So now the EPA is doing a risk assessment. Hopefully it will be concluded by 2024, saying, are PFAS a hazardous substance? What should we do? We don't know. So that's going to have an impact on wastewater treatment plants and what they do with their biosolids, how they remove PFAS from the biosolids to then land apply. And land applied biosolids help us cut down on fertilizer. So it is going to be a ripple effect, but we'll see what happens there. But that's going to be interesting for future regulations with PFAS and biosolids. So all that's leading up to this project that we're going to talk about today. It's a National Science Foundation funded project. We are going to work with the Water Tower in Gwinnett County, Georgia. Gaia worked at the Water Tower, or worked with them, and so they're great people to work with. It's a nonprofit global innovation hub in Beaufort, Georgia, about 40 miles northeast of Atlanta. They have 4 different pillars to their organization. They have applied research, technology innovation, workforce development, and community engagement. We're going to be the applied research sector. So we're going to work with Melissa Meekers, the CEO. She was also previously at the Water Research Foundation. We'll work with Kristen van der Hevel, as well as Chris Terry, and he used to be at the EPA. So these are great folks to work with, and we're excited to go and work at the water tower. They have 3 different wastewater treatment plants and 2 water treatment plants that they operate and own. We will work with the F. Wayne Hill Water Resources Center. It's a 60 MGD membrane plant, so it takes wastewater from the surrounding communities, treats this wastewater, and then sends it to Lake Lanier. Lake Lanier serves as their drinking water source for the surrounding communities. So what type of reuse is that? 3 options. Indirect, that's right, indirect, because you have that environmental buffer. Good, you'll do good on the quiz. So Gwinnett County has almost 3,800 miles of distribution system, 3,000 miles of collection systems, 220 pump stations, 1,500 miles of stormwater systems. So they have this network at their capability to help applied research. So researchers can come and do work, and it kind of bridges that gap between academia and industry and public utilities. So it's a really innovative partnership. So we've mentioned PFAS. We've mentioned they've been around, they don't go away, but we've only talked about a handful. We've talked about 6 maybe that are maybe regulated. There's almost 15,000 PFAS compounds out there. We've been talking about 6. So there's an unknown burden to wastewater treatment plants, to the drinking water plants, that we just don't know because we cannot detect. That we don't have the methods for it. The methods for detecting those 6 PFAS, you have to use an instrument called an LC-MS, a liquid chromatography mass spec. It's very expensive, very time consuming, hard to analyze. PFAS leaches from everything, it's in everything, it sticks to everything. So these instruments and the methods are very complex. So, and you can't detect all of them. So we're gonna look at a total fluorine. So if you think of carbon, we're good at thinking about carbon. We measure total organic carbon, and that can give us an idea of the water stability. It can give us, with the removal, it can give us an idea of DBPs that'll be formed in the distribution system depending on how much chlorine you add. So it's this bulk measurement that can give you insight into what's going on with the water quality. So we want to see if total organic fluorine can kind of do the same thing. If you have total fluorine, you can break it down into inorganic fluorine and total organic fluorine. Total organic fluorine are going to be PFAS-related organic fluorine bonds and non-PFAS related. So that organic fluorine, carbon to fluorine bond, it's very rarely going to be just naturally occurring. So it'll be PFAS impacted, or it'll be non-PFAS like pharmaceuticals, personal care products. So that bond is very rarely just naturally occurring, so it can give us some insight into the pharmaceuticals, personal care products that are in the water, but it's not a specific detection. So within that organic fluorine, you have AOF, adsorbable organic fluorine, which will include PFAS and non-PFAS. You'll have extractable organic fluorine, and then total PFAS-related organic fluorine, and then you have those targeted PFAS. So that's kind of the breakdown. In order to measure adsorbable or extractable organic fluoride, you can use the combustion ion chromatography. So this is combustion IC, and it can measure your AOF or EOF. The water tower has this instrument called the profiler that we'll use going forward to measure extractable or adsorbable organic fluorine. So the hypothesis for this project and the objectives, we hypothesize that AOF can serve as a tool to help quantify this unidentified PFAS present in water systems, but they're often excluded when we look at targeted PFAS analytes. And then we want to look at developing a standardized AOF method that can help close this fluorine mass balance for wastewater and water reuse scenarios to help abate that underestimation of PFAS contamination. And then we have 2 objectives. We'll work with the water tower in Georgia. We'll learn the different methods that they have in their labs. We'll share the methods that we have in our lab, and then we'll look at AOF and PFAS analysis. And then we'll look at a wastewater treatment plant and try to figure out what's coming in and what's leaving. We'll close that mass balance loop on organic fluorine and PFAS. coming in, are the PFAS going to the sludge? Are they going to the biosolids? Are they going to the effluent? So we're going to take samples at all the different points to figure out where the PFAS and organic fluorine's going, and then the next step of, okay, what do we want to do with it? So we'll take a sample. We'll take our sample from the wastewater treatment plant. We'll take it to target analysis of 17 PFAS compounds. You have to run it through solid phase extraction, and then you can analyze by the LCMSMS. And then we'll also take that same sample and we'll run non-targeted analysis of organic fluoride levels. So this will measure EOF. Well, we started with EOF, but it turns out that AOF, the absorbable organic fluorine, has turned out to be much more promising, so we'll probably stick with that. AOF, you would pass that sample through activated carbon. You would rinse it to remove any of the inorganic fluoride, and then you can run it on the combustion IC. There is currently a draft method in the EPA for this. It's method 1621 for total fluorine and then total inorganic fluoride. This is a draft method, so it's not been published. So we're going to work hopefully to get this method to have more than one lab that can reliably do this method to get it not just draft form, but an actual EPA method. For the 17 PFAS that we're going to look at, we'll use EPA method 533 and 537.1, which are out there and that are established to look at these 17 different PFAS coming into the plant and then where they're going in the biosolids versus the liquid effluent, and then comparing that with the absorbable organic fluorine to figure out if we can close the mass balance. So this is the wastewater treatment plant that we'll be sampling, and so we'll try to sample coming in and then after each unit process, the liquid train as well as the solid train. So I was like, can we sample at all these locations? They said yes, so we're going next week. So hopefully we'll be able to sample at all these locations and then measure the organic fluorine and the 17 PFAS at each of these locations. So the next step, so this project is just now beginning. So next week, my grad student Sarah and I will travel to Gwinnett County and we'll go work at the water tower and at this treatment plant, and we'll continue sampling throughout the spring and summer of 2024 and 2025. So I don't have any results from the project today, but hopefully we'll do this again next year and we'll have more results. But we'll collect samples from the Wayne Hill Water Resource Facility, analyze it for PFAS and organic fluorine, and then we'll work to hopefully develop a standard method for AOF. Combustion ion chromatography is typically a little cheaper and easier than LCMSMS, so maybe it could be more useful for utilities. We'll investigate to figure out if that's the case. All right, and with that, that's all I have, and I'd love to answer any questions.